This is Mastering Mathematics with your teacher, Karen Weston.
Hello, welcome back to Mastering Mathematics. I'm Karen Weston, your teacher, and this is a program sponsored by the Ministry of Education and ABS Television. This term is a crucial term for students. It can either break or make them, okay? And the education program goes on because we are going to pass mathematics. I saw the 2013 January examination paper and it's the same old story. So it is now up to parents and students, because as teachers and educators and the general public, we are playing our part. There are some students in the secondary school who we still need to come on board and to work harder on this. This world is not getting easier, all right? But we have to put in the hours and to make certain that we are doing our best. The government is doing its best. I know that we're going to have ceremonies where you're going to be given what we're calling the iPads, etc. And the technology is being offered to students. We must make use of it. I don't want to belong to a profession which has been described as actually accelerating poorness in this country. I want to make the poor richer, not poorer. But you can do it if you put in the work and start making certain that education is a top priority. Parents, I'm coming after you because it's what you tell them, what you carve out for them, not no role model. You're the biggest role model, and it is time now for you to start taking education seriously and making your children believe that they can achieve. It's not too hard, but you have to put in the work. The discipline must come. Today, what do we want to do in mathematics? We want to take you back again, because in the last week we completed all matrices, introduced the topic of vector, and we are going to continue in that vein. The vector topic is too easy. We cannot afford you to say that no, you don't want to do that topic, because as you're going to see in the second term, most of what we're doing in mathematics is like child's play, because it is coming and taking care of diagrams, getting your information, you're learning your definition, and then we're going. Last week, we started our topic with our vector. We got as far as telling you about where the vectors are used, and again we say it's for tracking, it's going out as a search party, locating people, locating space. It is used in the traveling world, on shipping and in aircrafts. That is why it is important, okay? Defense Force and the armies and everybody who has any sort of thing in terms of saying traveling must make use of this. Right. We made the contrast the last time to tell you that in terms of this topic, the vector is relying on what we would call the framework that we call the X and the Y axis, and we use the Cartesian plane in the classroom to show you the theoretical aspect of it. There are two words I gave you last week, and yes, we use the word coordinate, and we say in terms of a coordinate, we can say, and today I want to thank my nephew Ezra. He has made this so very neat and nice, because I had a little graph paper showing you. But I know you're going to say, Lord, Miss Weston, that's too small. So I have made it larger for you, okay? And thanks to Mr. Ezra Weston that he, in his lovely hand, has carved out this for us on the blackboard, on a manila paper. So in our classroom, teachers do not say they don't have graph papers. Let them do the drawing, and you'll be surprised to show you that you may find that the talent for some of them lies within this aspect. All right? Good. So on our graph paper, what we're actually saying, when you get into the examination room, one of these squares would be equal to 1 centimeter. And that is the sort of thing that we're using, that you can be counting 1, 2, 3, 4, etc. depending on the scale that they're asking you to use, because we know we can't have things as a real life situation, so we have to use a scale when we get into our classrooms. But let us therefore get back to our coordinates. We say if we have graph papers, we can put a point P. So I can say I can have a point P here, all right? And if I'm drawing it using an axis, so I can have an axis, and I'm going, and of course we know the horizontal position will be the x's, and the vertical position would be the y's, okay? When we are actually placing the coordinates, what we do, we write the x number first, and then the y number second. So for this one, if I had that this was 1, that's 2, and I'm counting up in here on the y-axis in 5s, and I'm going up 10s. If somebody had to ask me, and I had a point P here, and somebody had to ask me, what is the coordinate of P? First, I would be going from the origin, which is O, and the origin occurs where the two axes intersect at right angles, okay? And then I would start counting. Yes, if I'm going in the right position, I'm going in a positive direction. So a horizontal movement would take me over, and I come over to 1. And how do I get P? Yes, I have to step up. And according to the scale I'm using, I would have been up 5. So that the coordinate of this P here would have been 1, 5. Okay? The coordinate of that P would have been 1, 5. So let us use those letters, 1, 5. The 1 refers to the horizontal movement, and the 5 refers to the vertical movement. So we have to go, we are walking right or left, we're going to the right, my right here, and I stayed at 1. When I got here, I said, P, I'm looking for you. And I said, where are you? Am I going up or down? And I had to go up. And going up, I am up 5, okay? It could be 5 centimeters, 5 meters, whatever they had told me was the units they were using. And so when I have to write the coordinates now, my horizontal movement first, which is 1, and my vertical movement, which is 5. Now, if I have to use the same coordinates to translate them into position vectors, all it means, instead of writing just P, position vector starts with 2 letters where I have OP. So it says I have to start from the origin, and the numbers are the same, the actions are the same. We're going to walk in a horizontal position, so we're going to go 1, and then again we still have to go up, and it is 5. So once we have the coordinate, we know the position vector, because all we have to do is to represent the row vector as a column vector, and the 1 goes on top and the 5 at the bottom. That is all it is. When I show you the exam paper, you're going to see the questions would have been saying, given the coordinate R is equal to something something, T is equal to something something, find the position vector. And it could not have been easier. All you have to do, you say, well, they gave us in row, and now I have got to give them in column. So that is all we do. Okay, so that is the position vector. I want to come on now to a term that we use in vector, and we start again in terms of geometry. We talk about parallel straight lines, and then again in terms of the vectors. So yes, we say 2 lines are parallel, they extend in the same, not the same, they can be going in opposite direction, but they do not meet. Okay, so I can have them going here. Okay, so they're extending without meeting. What do we mean when we talk about parallelism when it comes to vectors? And this again takes us into our branch where we are actually doing some. It can be taught and called for the little children in the primary school where we have to simplify vectors. So for example, if I gave you this, that I had a half, okay, what are the equivalent fractions that would have given me a half? And we can call some of them, because even my friend Aisha in here could tell me that it could be equal to 6 upon 12. How can I get a half again? It can be 50 over 100. Yes, Aisha, what do you have to tell me? Because Elizabeth is not here. Oh my, she's probably helping out at school today. So I'm on my own. Jetta, what would you tell me? How can I get a half? Because your sons and daughters are watching, you know. So here we can have 4 over 8. All right, so those are the 3 things. But how do we know it is a half? Because we have to look at see what is the common factors. So let us write them for you. So I can start with a half, and for the 6 I can have a half. For the 6 over 12 I can have 6, and it's times a half, okay. And for the 50 over, again I can have, it is 50 and it is a half again, okay. And then for 4 over 8 I can have that it is taking out 4 and I'm left with a half, okay. Because again, what did we say? These are called the numbers outside. Oh, let's write them properly so that you can see they are. Let's leave them like this. Let's not put them like no fractions, because we want to translate them now into vectors, so that we're saying from the x value we're taking 1, this would be a 2, and from here again it is a 1 and it is a 2, okay, 2, so it's not here, okay, and here it's a 1 and it's a 2. So I can give you, so again, I'm not just taking about fractions now, I'm talking about vectors. Okay, so I can have a vector A, which is equal to a half, B can be equal to 6 over 12, C can be equal to 50 over 100. Okay, so let's remove our idea of fractions now. Yes, that was just to give the school children an idea of what we're doing here. And that's 4 over 8, so that this is now D, is equal to 4 over 8. And what we were actually saying is that from each of these brackets, we can take out a 6 as a common term, and then we'd be left with 1, 2. From C, so this came from B, then from C, I can have 50, so I can take 50 and I would be left with 1, 2. Again, from D, I can take out a 4 and I would be left with 1, 2. What do we notice? What do we notice? We notice that when we have that, everyone has in common a component of 1, 2. Can we see it here? Here, here, and here. All right. And we had our first line, first of all, that little vector, which would have been here, where we have A, which would be equal again to the component 1, 2. What are we saying? Because this is going to tell us that A would be parallel to B, would be parallel to C, would be parallel to D. Okay? But the parallelism is coming, but it is, notice that that B would be 6 times A, C would be 50 times A, and D would be 4 times A. As long as we have a common component, we would say that the vectors represented here, that they are parallel. So as long as we have a common component, the vectors are parallel. it will be parallel to A, but it is 6 times in length for B. Parallel C, parallel to A, but it is 50 times the length of A. D is parallel to A, but 4 times the length of A. So that is where parallelism comes in. Vectors are parallel. They don't have to be going in the same direction, but as long as they have a common component, and we can talk about it to say factorization, then we say that they are parallel. We have given you coordinates, position vector, and parallelism. We need you to take a little time just to construe what I just said, and then we will be right back to tell you about the triangular formula. Okay, and then after that we will have you doing a little exercise with them, because there's nothing difficult about this, and this is what we call mathematics. So go and get a cup of tea, a glass.
If you know the answer to a question is incorrect and you cannot find the mistake, start over on a clean piece of paper. Oftentimes when you try to correct a problem, you continually overlook the mistake. Starting over on a clean piece of paper will let you focus on the question, not on trying to find the error. Always read math problems completely before beginning any calculations. If you glance too quick at a problem, you may misunderstand what really needs to be done to solve the problem.
Right, so the first thing we did today was our coordinates, and we know what that is. We did the position vector. So the difference between coordinates and position vector, we're always starting from the origin for our position vector. Parallelism, what did we say? If we have a vector and we have a component that it is 1, 2, and we look at other vectors and we can see they have given us B is equal to 6, 12, C is equal to 50, 100, D is equal to 4, 8. We can look and see, we can take out a common factor, and each one would have a similar component of 1, 2. As long as that is possible, then those vectors are parallel to A. Each would be, so B we had said would be 6 times the length of A. C would be 50 times the length of A. And D would be 4 times the length of A. And that is all parallelism is about. All right, so we are now down to where we're talking about a triangular formula. Now, most people like to tell you that you can, there's a parallelogram law in terms of the vector, but I just like to say that because the parallelogram can be split into 2 triangles, so I like to say that all vector questions can be solved using a triangle. Now follow me with this little story. You know we have our children in school. What is the thing that they love to do? You can't leave your keys in your car and say that you have forgotten them. Worse if 2 teachers did that. And we have 2 children outside really looking at the vehicle. All right? Because you know what they're going to do. Let's go for a test run. Okay? Suppose they got away with it. Right? Look at what would happen. We would have, so his name is John. All right? And of course, challenged by a girl, Cheryl. Okay. What did they do? So John took up the car, went down to Cheryl's house. Cheryl got into the car, another car, going on the road too. Now, poor Karen coming home after a day at the ministry and coming in this direction, and what do you think happened? Somehow Crazy John and Cheryl got it in their heads that they should go after and go for a race. None of them can drive properly. So what do you think happened? In trying to pass one another, bam, everything happened. Accident, car, accident, the two of them. And what did they do? Crash into poor Karen coming home, going home. So those two blue car people crashed into the poor Karen going home to rest. The two people who were driving, they represent the sides. Oh, this one is not right. We have to get rid of that. Yeah, the sides of the triangle. So we have side 1 and side 2. And where Karen is coming home, this is side 3. Okay, side 3. So we had a big mashup there. So what did we have? We had S1 plus S2. The full weight went down on poor Karen. Okay, went right into S3. So we know right away. So that is what we're getting. However, when we're thinking about this in terms of vectors, we call the arrow going in the same direction, we call them the sides. And the arrow that is coming in the opposite direction, we call it the resultant. Okay, so it is very much like the right angle triangle, where you can think, just to make an association, it's like the hypotenuse, okay? And the other ones would be your opposite and your adjacent sides. So similar thing, it is not the name, but I'm telling you that you make that association, but you're looking again to say the hypotenuse part of it will be coming in the opposite direction. That in the vector we call the resultant, and the adjacent and the base that you're accustomed to about when we're using a right angle triangle, we're calling side 1 and side 2, because the vector does not depend on any right angle triangle. Okay, so our formula for the triangle would always be saying that the resultant is equal to side 1 plus side 2. And then of course to find any of the other sides, it would be equal to the resultant minus the other side. Okay, so if we wanted to find side n, it would be minus the other side. So two formulas we have to know in terms of a triangle. There are 3 elements to it. We have resultant, we have side 1, side 2, and then we treat it as if we were treating the hypotenuse, that h is equal to p squared plus b squared. But here there's no square or anything. All we're just saying, the resultant, which represents the vector going in the opposite direction, is equal to the sum of the other 2 sides. So we have resultant is equal to side 1 plus side 2. If it's side we want to find, the side then, because this will be the big one, so the side then will be equal to resultant minus the other side. I'm going to come to show you how we do some of this, and you're going to see that that is about the biggest thing that we have to do when we get to this topic that we are calling vectors. That is what we have to do for the examination. There's only one other thing I have to tell you about, and that is called collinearity. Okay? But there is nothing else. So there's one more word that we have to use with the vectors, which I am going to call collinearity. And again, I said they should have left us with those Latinians, because you would see right in there, you're seeing collinea, okay? And you know right away what that is going to mean. So we're going to tell you about that term. But before we get into that term, collinearity, let us go back and show you how we are using some of the things that we have talked to you about today. You see how those diagrams look, okay? What we have just said is that we talk about the coordinates, and this is the topic. We know where we're using it. We know they use it, all right? So we can be geographers, we can be trackers, we can go into the desert, we can be on an airplane, we can be on a boat. Somebody's lost at sea. We need to do these things, and that is what the Fullers used that time to guide that boat that was sinking into Barbuda. Somebody could locate them. That is what did not happen when the last boat was lost, because they had no vector tracking, and although they were so close, yet they were so far. So these things are so important. So we have the coordinates, we have a position vector, and we know right away, as long as we have coordinates, we can find our position vector, because we change the row vector into a column vector. Then we talk about parallelism, and for those of us, it refers to something as if we're saying what are the equivalent actions, but we know that they are the components. Once we have a vector, if we get all of them with the same single component, then we know that they are parallel. They may be in length, and so that is where that is coming. Then we told you about the triangular formula, and of course we know two cars racing in the same direction go on crash. Old man going home to rest, so the old man would have taken the blood work for that particular one, and that is called the resultant, so that the resultant would be equal to what we're calling side 1 plus side 2. If we wanted to find one of the sides, it would have been the resultant minus the other side. We're going to leave you here for tonight. You're going to go organize, check, see that you understand it, because tomorrow we'll be taking you to work some of these problems, which is all CXC asks you to know. Again, we'll also be addressing our school children tomorrow and the teachers in the primary school, because I know what they're talking about right now. The project, Miss Weston, the project. So we're going to address that for you too. Have a good evening, and keep on listening to Mastering Mathematics. And remember, school children, grannies are competing with you. I don't care if they win out, but you better not make them win out, so you better work twice as hard. See you tomorrow.
Join us next time for another in the series, Mastering Mathematics, a production of the Education Broadcasting Unit in the Ministry of Education and ABS TV.